Great. So, Phantastic Code Smells and where to find them. No, there's no image missing. I picked that one on purpose because Code Smells is sometimes it's about not really having an image about what's going on in the code. So I thought it was quite fitting. And I couldn't find an actual image that would fit like the description. So, okay. My name is Arne Mertz. I'm a software engineer at Züge Engineering. I work mostly in embedded projects. I've done some enterprisey projects, but currently it's more like embedded Linux, real-time operating systems, that kind of stuff. Besides those projects, I'm also a trainer for modern C++ and clean and maintainable code, in-house and externally. So, what's a code smell? This is, well, one of the definitions I could find from Martin Fowler. So it's a surface indication that usually corresponds to a deeper problem in the system. So let's take that apart. Surface indication means we can find the code smells. They are usually relatively easy to spot, but they are not the actual problem. That's what we should keep in mind, because very often I see people like, oh, that's a code smell, so you have to get rid of it. It's not the actual problem, so if a code smell is not a problem, why get rid of it, right? Corresponds to a deeper problem. This usually means like we have like violated some of our principles, solid principles, single level of abstraction, single responsibility principles, or we are missing some patterns, something that makes our code more readable, safer, missing some abstractions maybe. We will see a lot of this later in the talk. So in general, this usually means we have some kind of maintainability problem. And also, the word usually means, again, it's not always a problem. So having a code smell does not necessarily mean I identified this code smell, we have to fix it right now. But it usually means we have to maybe dig into it and see if we actually violated some of the principles, or if there is a pattern we could use, and then see if it improves our code. So I've picked some example codes from open source projects. This one is from SFML. It's a simple and fast multimedia library. You can find it on GitHub. And this is an example program where they show basically one example how to use mostly the graphics parts. I have to say up front, this is written in C++ 03, so we won't go into like missing C++ 11, 14, 17 features and the like, but we will come to a few pieces later, but mostly this is about more general code smells, not depending on the language features. So let's have a look at the code, see if you spot the problems. Okay. So this is about 240, 250 lines of code in the main function. The result looks like this. This is Pong. And, well, this is URL where you find the source code. So the first problem, the first code smell, which is a really common one, is the long function. As I said, code smells are surface indicators, so the surface indication is it is a long function. What we also have really often is like these blocks of code, like here we create a ball and set some properties in it, and here we create a rectangle and we load a text font, and you have like blocks of code with an explaining comment above what is going on in these next lines of code. And the deeper problem is that this kind of code usually violates a single responsibility principle. So the main function should do one thing. Well, people often say, well, why? I mean, the main function is the whole program. It should do basically everything that runs in the program. But it should have run responsibility, like setting up the application and running it, and that's it. And not like constructing some shapes and setting colors and stuff like that. So this is also the single level of abstraction that is violated. The main function is at a really high level of abstraction, and these kind of details are really low level. So we have to do something to make the main function a higher level and get this one to some other place where it's lower level. So, but I said, well, the function is too long. What is too long? It depends on what's in it. And that's a huge problem for those people who try to use tools like, yeah, I want to detect a hard border, this is too long, this is not too long. We really can't tell, and we really can't use tools that say, this is okay, this is not okay. I mean, we can have like hard limits. If I have a function that has 100 lines of code, this in nearly all cases it means it's really too long. But I can have like a function that has 10 lines of code, and that's already too much because it's just violates one of those principles again. On the other hand, I may have a function that has like 20 lines of code, and that's just about right. For example, this one is another example from Qt, where they have like, well, some kind of window and a cursor, and they do like many lines of code on basically the same level of abstraction, like cursor, and insert this, insert that. You could argue you can break that up into smaller pieces, yes, but in general, like these lines of code from here to here is about the same level of abstraction, and in a code review, I wouldn't mark that if you had like a function with these lines of code. So this is about 15 to 20 lines of code, which would be okay. On the other hand, if I have another function that's where the whole purpose of the function is just to return a value, then basically more than 1 or 2 lines of code is too much, because then it does more than just return some value, right? So it's not quantifiable. I think there are tools which have like soft borders, where you have like, okay, above 20 lines of code, I generate a warning. About 80 lines of code, I generate a hard error. But still, we usually want to get rid of all our warnings, so this is basically a hard border at 20 lines of code. And still, 20 lines of code could be okay, or could be way too much. This is another one from the SFML library. We have an update function for shapes. It just does like several lines with counting the points of the shape, the vertices, updating some vertices internally. And then it suddenly calls update fill colors, update text chords, update outline. And it has these useful comments where, well, color, the name of the function is actually more detailed than the comment. So the comment is like, just throw it away. Outline, well, the comment says basically the same as the function name. And texture coordinates, here the comment is more detailed because it's not abbreviated than the function. And all the stuff above, well, it's just something about vertices. And it's a completely different level of abstraction again. So when I refactor this, what can we do? We can factor out functions, take blocks of our code, and put them into different functions and give them meaningful names. And if I have like these blocks of code with some comment over them, in this block of code this and that is happening, this is usually a good start for a name for the new function. So if I take this one, okay, don't take these single blocks of code and make them into a function name, but I just say, well, updating a shape means updating the vertices, the colors, the coordinates, the outline. How this is done in detail, if you need to know it, we can get into the function and read it. But if you don't only want to know at a higher level what is affected when I update my shape, This is it, and this is all I need to know. Or the other one, the one we had before, with the shapes, with the rectangles and so on. We have a left pedal that is a rectangle, we have a right pedal that is a rectangle, and the only difference between these two blocks of code is the fill color here. And there's another smell in here, like magic numbers, like 200, 100, 100, and 100, 200, 100. It's not that easy to see, and if you don't know your RGB by heart, then you don't really know what these colors are. So when we refactor this, we have like static constants, and then we create a pedal in dark blue and one in dark red, and we create the ball. Also, if we have data and functionality that is associated, especially if you have like more functionality that deals with these rectangle shapes and with this ball shape, there is a good idea for complex functionality to use classes. Because, well, you probably didn't see it when it scrolled through, but later in the game, the ball, when it hits something, it makes a sound. So we probably want to associate the sound with the shape, so it does everything in one place. What's the problem in this code? Why do we have to parameterize the ball with the color white? I mean, we do have to do this with the pedals, with the rectangles, because we have a blue one and a red one, but the ball is always white. And this is yet another code smell that we see relatively often, especially in larger projects where we don't know where the direction is of where the project is going, where it's going to be in a few weeks or a few months or years. We generalize, because what if we want to change the color of the ball? So we just go ahead now and we add this constructor parameter and set it to white. So maybe in the future we can change it. This is called premature generalization, like this what if. What if I need to add a hook here or a hook there? This is something we see very often, that like generic function gets called in some places because someone could be interested to be notified when this happens, but we don't have anyone to notify just yet, so we just call a no-op function. Or we go ahead and say, well, I have this functionality and I just need it for integers, but maybe someday someone will come along and needs it for like doubles or for something completely different, so I make it a template. The problem with this is, first of all, it's KISS and YAGNI. Those are abbreviations for keep it simple and stupid, because the simpler the program is, the better I can reason about it, the better I can read it and know what's happening. And YAGNI means you ain't gonna need it. Because if I parameterize the ball with the filling color, then probably the filling color will stay white forever. But the thing, I didn't parameterize the ball with like the size or something to make it easier. That's the parameter I don't have here. But it's not a requirement for now that I have like a sizable ball or a ball with a different color, so just leave it out. If you have to add it later, then add it later, but not like speculate what could be in the future without knowing it. On the other hand, if we know now, like I have this feature on my in the next milestone, I have to add this or that feature, then I can structure my code in a way that makes it easy to add that feature. But until I really have the requirement, I have to implement the feature now. There's no use in like preparing the things and add parameters that might be used in the future, because well, most of us work in an environment where requirements change. So if we add the hooks and the parameters now for the requirements that might come in 2 months, then you get a requirement change in 1 month, and we have added complexity that we never need. We also have to like test this kind of thing. For example, this ball, if I set the color to green and maybe I have a parameterizable border and I set the border to off, then I have a green ball on a green background, and either I test it and then I see that there's a problem, and then I even add additional code to my project to check that this color is not green, it's something visible, which I'll never need because the ball is ever going to be white. Or I don't see the things, and then at some point someone is setting the color to green, and people are complaining because I can't play the game anymore. So the fix to this is basically, if you have like generalizations and that are not really needed, leave them away. Structure the program and the code in a way that makes it easy to add them later, but don't add them when you don't need them. Next code smell, same game, is still Pong. This is basically the start, more or less, of the main game loop. What's the problem here? Deep nesting, exactly. We have a while, so while our game window is open, we pull events from the window. And while we are pulling events, if the event we are currently having is a space or a touch, and if we are currently playing and we do another while loop and like do some stuff with angles here to make sure that the ball doesn't go like perpendicular, but in a certain angle. This is like, again, deep nesting means we usually have a violation of single responsibility. This is way too detailed for one game loop. So again, single level of abstraction is violated. And we are very limited. While we are reading code, people say like, we have like 7 registers in our brain, and we have to overload them all with all those facts. What's the condition for the outer while loop? What's the condition for this if and for that if? How did we get here? And we all have to keep this all in mind, and it makes it much more complex for us to actually go there and read it all, instead of having like this function at one level of abstraction. So again, one of the fixes is factor out functions. Factor out the contents of the loop to another function. Also for ifs, we can very often like check if some condition we need is set, and if it's not, we just return early. Like very often you see in code like, if I can open the file, and if I then can read a string from the file, and if then the string has like more than 20 characters, and if the string is then parsable as XML, and if that XML has like this or that tag, this is way too much. If I can't open the file, go. If I can't read a string, go. If the string is too short, go. And I just get all those special cases where I can't really do anything. I just get them out of the way, and then I do the real work, and not like indent it like 20 times, but this is my main functionality. So this game while loop, if we refactor it a bit more, then all the internal indentations we had is like handling events from the window. And then when we go through the loop further, it is about like 150 lines of code, what's the original loop, then we see then if we are playing, we move our entities, the ball and the pedals and so on, and in the end we redraw the window. If we do this, we see a very common pattern we have like in software engineering, in embedded software, like everywhere. Get inputs, process them, generate the outputs, repeat. If you don't refactor this like this, we just see we have like a giant loop, but we don't really know what's happening there. Next code smell. It's an if. That's what we see. And then there's like a bunch of stuff going on. What is this doing? No idea. I mean, maybe someone who does like this kind of thing, like working with coordinates and geometric shapes very often sees what's going on here, but honestly, it took me like a few minutes to go to figure it out, even with the comment. Okay, we checked some collision. I see we have the ball, we have the left pedal, and somehow collisions are checked. How do we refactor this to? Well, the actual problems is this is again too much detail. We want to know if there is a collision or if there is no collision. We don't want to know the exact details how we figure out if there is a collision, right? So this smell is called complicated Boolean expression. It also is applicable to basically all kinds of expression. When they get too complex, we can't really figure out what's going on there. And the fix is, well, factoring out variables or functions. Sometimes it's enough to factor out variables. I can tell you right now, this is too complex to just deal with variables. So what we want is, if the ball hits the pedal, that's what's basically done here. The ball hits the pedal if the ball touches the pedal on the left, and if the ball is the same height at the same height as the pedal, right? So those names are not really good, but this is basically just the first round of refactoring I have done just to figure out what's going on here. So the ball is at the same height when the ball is above the lower edge of the pedal or below the upper edge of the pedal. And the ball touches the pedal of the left when the ball is basically, well, going into the pedal and so on. And, well, we have the upper edges, lower edge, the right edge from the pedal, and so on. And these are, again, coordinates, and these all together make up the expression we have seen before. So, well, if I have, like, my function, and before I have the if statement, I have to put there, like, what's this, 12 lines of code, 15 lines of code. That's, again, getting a long function, that's too much. So this is way more readable, and this is the level of detail I need to know if I want to know when is this going to happen, whatever is in the if block. So there's a but, one that I hear relatively often. That's a lot of code. It is. But it's also a lot of detail that whoever has written the code in the beginning has made up in their mind, has calculated. So they have not thought about, well, I write this expression and I'm done. They say, well, hitting the pedal means the ball is at the correct height, the ball is at the correct x coordinates. This again means I have to compare these and those coordinates. So basically these variable names, it was what's going on in the developer's mind when they were writing this. And then they have simplified it by just inlining everything. So for all the people who come later and who have to read the code and who have to understand and basically recreate what the developer was thinking, it's a very good aid to have like these variables and the names and the functions saying what the people were thinking, and then you can more easily spot errors in the thinking than if you have like this big expression and you don't know what's going on. The next thing, what's about performance that can't be good for performance? First of all, how do you know? Lots of things I hear about performance, especially in this kind of scenario, are myths from the 60s, 70s, something. Also the early return stuff I had earlier. No, you can't early return from functions. Single entry, single exit. Yeah, that's something completely different. That has nothing to do with performance. The second thing is, does performance matter? In this case, I mean, it's a simple game of Pong, and we have like a game loop, and we don't want like the ball like going really fast, so we have like time between all the iterations. So performance in this case doesn't really matter. I'm not into financial trading or high performance stuff. Their performance matters. It's okay. But there's still two advices. Trust your optimizer. They're getting better and better and really doing incredible stuff. And then the next thing is measure and use a profiler. Not only to figure out if what I actually did there impacts performance, but also if it matters, if this is really my point of contention, my bottleneck. Mostly when people whine about performance, it's like more like, yeah, I don't want to type all this stuff. There's like a build and development smell. It's lack of tooling. Sometimes we can't go without the proper tooling. Well, compiler warnings, it's mostly accepted these days. Optimizers and profilers use them. Especially profilers, I think, are for people who really care about performance. They have to use them. Others who pretend to care about performance don't use profilers, maybe. So if performance is an issue, use profilers to find the performance bottlenecks and so on. Static analysis, use sanitizers, run your tests, especially your system tests and so on using sanitizers to find memory leaks, undefined behavior and so on. And use your IDE tooling. It makes everything so much easier. The refactoring, like factoring out a function is just selecting a block of code and just say factor out function, type in the new name and it's gone. Typing all those long variable names that are really descriptive. Type 4, 5, 6 characters and the auto-completion will help you. Okay, so much about general code smells. Let's start with C++. This is yet another open source library, libsass. Thank you, Christian, for the tip. The right part is still from the Pong game. Remember, it's C++ 98 or 03, both code bases. But what's the problem here? If you look at the right block of code here, we have like some hints. Well, pi is a constant, the width of the game is a constant, the height of the game is a constant, the size of the pedals is not a constant. Why not? The radius of the ball is not a constant. Why not? And on the other side, we have like getters. Those are methods who usually should not modify the object. They are not marked const. We have like this toString method which is marked const, but then the string conversion operator, which does nothing but calling the toString method, is not marked const. Why not? It could be. So the smell is missing const and missing const expr when we are using C++ 11, 14, 17, and so on. I mean, seeing missing const, okay, this is a smell. What's the actual problem we have? The problem is we don't have really clear semantics. If I see the pedal size isn't const, if I see it's const, okay, so I know it's a constant. In C++ 11, I would, even for the vector 2f, for the two-dimensional vector, I would expect this to be const expr. But if I see it like this, at the beginning of my main method, that might mean that at some point in my game the pedal sizes are varying. Or the radius of the ball is changing or something like that. So this is like, I'm wondering what's going on here. The same if I have a function, a method that is not marked const. The first thing is I can't use it on const objects. And then that probably means that I don't mark object const, even if they theoretically could be, even if they are never changed. And then I'm not really clear about what is going on here. Do I modify these objects, or are they only not marked const because someone didn't want to mark them const or didn't want to make the methods const? And in general, querying methods should be const. They should not modify the observable state of an object. This I explicitly say observable state of an object because sometimes we have like internal state of an object, but methods like get an area of some complicated shape or something that first have to calculate the area and cache them somehow. Those kind of caches and mutexes and things like that should be mutable, and then I still can make my object const and the methods const. There was a talk by Jason Turner at the CPPCon where he does really much more detail about const and const expr. It's a really good talk, I think, where he talks about C++ code smells. So I explicitly went ahead and tried to pick code smells he didn't do, but const I think is too important code smell, so I just didn't want to skip it. This is a software development kit, also C++ 03, I think, even if they don't state it explicitly, for some embedded sensor stuff. The hardware vendor basically made their software development kit public. So this is again an example program how this stuff is to be used, and they have like a while loop where they probably have someone break in there to get out of the while loop, and they process something with sensors. And you see, like in the end of the loop, if the sensor is there, then I have first to disconnect it and then delete it, and if the other sensor is there, I have to disconnect it and delete it. But what happens when I basically exit the while loop with an exception? Well, therefore I have a try block and a catch block, and in the end, I have to check everything again and do the same thing over and over again, disconnecting, deleting. So the smell here is missing RAI. RAI usually is the abbreviation for resource acquisition as initialization. I don't know who coined responsibility acquisition as initialization. It's a bit broader. But I think it really matches the thing, because it's not only about leaking resources, it's about, cleaning up everything, like resetting anything that needs to be reset. Imagine, for example, I have like a calculation going on, and I have like this waiting cursor, and when somehow the calculation breaks, I want to go back to the normal cursor. I can do this using RAI. It has nothing to do with resources. So the problem when we see that there is no RAI in place is basically like we see we have cleanup code written manually, and usually if you have some manual cleanup code, there probably are places where we have forgotten the cleanup code. I've seen it in an earlier project where I've worked, where they had like some borrowing, freeing mechanism, and at some points there were like problems where they had like missed a count, and then they had the function like not only free the function, but free the function even if the reference count is still 1 or something like that. So they knew there is a resource leak because I missed my reference count by 1, and then they inserted a special function to make this cleanup possible. So using smart pointers and similar things from the standard library can alleviate that. Actually doing cleanup in constructors like this disconnect we had here for the sensors makes this unnecessary to do this cleanup manually. And if you have third-party libraries that don't do a proper cleanup in the destructors, then we can write RAI wrappers for those classes to do the cleanup in our destructors. Another class, very simplified, from the ladder SDK. So what's the problem here? This class is actually copyable, because the compiler is helpful and generates copy constructor, copy assignment, and since C++11 move constructor, move assignment for me. What happens if I accidentally copy an object of this class? Well, the compiler generates a member-wise copy, so I have two objects with the same handle. Could be okay, could be not okay. But I have a destructor, and having a destructor tells me, well, this might mean that there's some cleanup to do. Could be connected to this handle, and if there's cleanup going on with the handle with that number, and I have a second object, then the second object either will try to access something that isn't there anymore, any resource, or tries to clean up the handle a second time. Both could lead to problems. So if I look at the destructor, there's like, if the handle isn't 0, then disconnect. This will get called twice if I copy the object. And the disconnect is some disabling the handle, closing the handle, so might be that I'm calling some closing routine on the hardware or something that may or may not be a problem, but this is something where we have to investigate. So the smell is violation of the rule of 3 or 5, depending on which language standard we are using. If we have one of the big 3 or 5, then we should define the others as well. The big 3, 5 are destructor, copy constructor, and assignment. Those are the 3. And since 11, move constructor and assignment. If I have one of those, if I have to define one of those, then I should define the others as well. And in many cases, I can always either default or delete them, depending on what I want to have. If I don't want to have the copyable thing, then I have to delete them. If the default is okay, then it's better to explicitly say copy assignment okay, default, copy constructor default, because then everyone else reading the code says, okay, the programmer says this is defaulted, this is okay, it's not an accident that this is copyable. So one exception may or may not be, this is open for discussion, if you have like base classes, abstract base classes preferably, then you can have like the virtual destructor defaulted in your base class. Then the only thing why you would do this and not touch the others of the big 3 or 5 is just to make the destructor virtual. And anyone who reads this, a virtual destructor is defaulted, just sees it's because it's to make it virtual and nothing else. Next, C++ code smell. This is in SFML again. SFML also handles input devices like joysticks. So this is, I think, for a Windows implementation for the joysticks, well, some method to check if a joystick is connected to inputs. And this is part of a longer function. You see, again, this one is line 511, and the if close it at line 672. So I didn't want to scroll again. What's the problem here? We have for loops with iterators over some collection. This is a vector of joysticks, or of joystick records. As I said before, this is C++03, so we don't have range-based for. But even in C++03, we have standard algorithms. And usually a for loop, a raw for loop, or a range-based for loop over a fixed collection can be expressed by standard algorithms. So why use standard algorithms? Why prefer them over for loops? First of all, those library implementers are really smart, and they usually have the correct for loop, so you don't have like typos and accidental errors in there. They also usually are really smart and make the most performant for loop you can do for this general case. And those standard algorithms also have descriptive names, mostly. So you don't have to figure out what's happening in the for loop, but you get a name and you know, okay, this is a sort. You don't have to look like in the for loop what's bubbled from left to right and so on and figure out that it's a sorting algorithm. It's when we write down standard sort, we know what's happening in there. So with C++ 03 not having like lambdas and so on, this is a bit more verbose. But the second function is basically, well, I'm looking for the joystick that has the same index as I put into the function. So I have the same index function object up there, callable object. It just returns true when the index is the same. And I take an instant of this one and put it into findIf. FindIf will return me an iterator pointing to the object that has the same index or to the end of my collection. And then here I did the one I said earlier, the early return. If I didn't find the joystick with the same index, well, then just return false. This was like, it's this return false down here. The rest, the 160 lines of code here between the index, the actual work that's happening inside here, starts down here. And we can use the findIf for the other loop that just checks, do I have something with the index or not? And in C++11 we can go ahead and use std any off, and then just go over the joystick list and insert a lambda here instead of just writing the function object separately. So the general advice is here, prefer range-based for over raw for loops with dealing with iterators, and even prefer algorithms over range-based for. Let's have a look at more loops. Well, I have some container with employees. This is my source, and I want to have a vector with employees because I want to deal with vectors and not with that other container. So I reserve enough space in my employees vector, and then I copy them one by one, push back. That's a range-based for, so we could just heard we should use algorithms. Std copy does the same thing. Okay? Now, standard vector has an constructor that takes two iterators and just does the copying. We don't have to use algorithms for everything. We have to know our library. So use the correct constructor, and you just don't need the algorithm and the thing. You don't even need the reserve because this constructor does the reserve for you if it can. Okay, so we have our vector of employees, and we now want to have their salaries and by a unique name. So we have a map from names to salaries. We could do it like this, but this will be like a slight performance hit because at first we have to like construct the pair, and then this is an assignment. So instead we could like choose emplace back or emplace, sorry. But again, this is a loop, so we should use an algorithm, right? What's the correct algorithm? Transform. Which one is more readable? I mean, the loop is relatively simple. I see what's happening in the loop. In the transform, I have to use, well, both the iterators, and then I have to like create some insert iterator for the map, and insert iterators for maps and sets lead like a hint iterator, so I give them the end or something else, maybe begin. And then I have to create like this lambda, either inline or beforehand, to actually say, well, when I have an employee, I want to have like this pair of the unique name and the salary. This is not only worse in readability. If you do like benchmarks, it's also slightly less performant, mostly because of this iterator. Because most of the times, if you have an unsorted list of employees, this iterator will point to the complete wrong direction, and like just taking the in place and starting at the head of the tree that is in the map is the better performing operation. Well, we usually have like managers who don't want the employees to know their salaries, so we have an additional requirement. Only if the employee isn't a manager, insert the thing into our map. What's the name of the algorithm? Sorry? Transform if. Is that one in the standard library? Nope. I mean, we have like lots of algorithms that have an underscore if, which do basically the same thing. Do the thing the normal operation does, but with a predicate, like copy if. Copy only the things that satisfy a predicate. So if you look at the GCC code, library code from transform, and copy if, and put away all the nasty metaprogramming stuff they do in there, we can write transform if. And then we can go ahead and use transform if to do our thing like inserting the pairs of names and salaries for everything that is not an employee. I don't think that's readable, right? So this is an example for, yes, raw loops are a code smell, but a code smell is not necessarily a problem. I think especially in the case of transform, the name transform is just so general that I take something and get something else. If I have like this 3-line for loop instead of this thing, I just see what's happening there. And this is one point where, okay, we have a code smell, but we leave it there because when we try to fix it, it gets worse. What about ranges? Maybe a bit more readable, but still, we like have to do these lambdas that create the pairs instead of just using in place on the map. So I would guess I would still prefer the raw loop in this case. That doesn't mean that when our managers get the next idea and come with the next requirement and the loop grows more, at some point we will have to go and say, okay, now we are getting to a place where maybe ranges or something else is more readable than the loop that has grown over time. So the smell still remains a smell, but not every smell needs fixing. At least not right now. We have to check later when we have to change the code. So this was basically more or less a, let's say, introduction to code smells. We had the long function, we talked about premature generalization, deeply nested control flows, complicated Boolean expressions, const expression-less code. Well, the more general smells, many of them can be fixed by factoring out functions, factoring out variables, giving them meaningful names, factoring out classes. The C++ smells not so much. There you have to like know, well, add the const, add the RAI classes, add the missing constructors or destructor, and try to replace the raw loops by algorithms and similar things and see if it turns out better, more readable. For the general code smells, there is at sourcemaking.com like a huge list, like I think they have like over 50 smells, many of them related to object-oriented programming, like deep class hierarchies and like using switch cases to simulate polymorphic behavior instead of just using inheritance and polymorphism. But the main thing, the most important thing is we have code smells in every code base. For example, long functions in any code base that is more than a hello world, we probably have some long functions in there. maybe not that long as the ones I've shown here, but like functions that have grown over time and now have like 40, 50 lines and could very well be split up. The examples I've shown are not necessarily bad code. There are code smells in them. They could be problems. Sometimes they are problems. And if they are problems, we should fix them. But that doesn't mean that it's really bad code. Because, I mean, you have to be pragmatic writing the code, because you can't polish your code until it gleams, because at some point you will have to add some functionality, right, and not refactor all the time. Code smells are not always an error. So if you see a code smell, not just there's a code smell, fix it, but just look into it and maybe add a comment, so this is not a problem here, or also those problems can go stale, and when you change the code and add more functionality, those code smells can become a problem. But still, we have to keep in mind, code smell is not necessarily a problem, but can be a problem. So we have to look into it. Also, being stuck with C++ 98 or 03 or 11 and not being able to use all the shiny new stuff we have in the newer standards doesn't mean our code base has to be dirty or smelly, and we still have things we can fix and things we can improve in our code bases. I already mentioned Jason Turner's talk. Also at CPPCon there was a talk by Kate Gregory about meaningful names, giving better names. Naming is a complete topic on itself, but it's also a code smell, like having short names, non-descriptive names, abbreviated names that don't mean anything for anyone. But I leave it with that. So that's it from me. Are there any comments, questions? I think we have a lot of time on our hands right now.
Hi, Arne. Thanks for the great talk. I totally agree with the actual smells, but I have one point. If you could go back to slide 13, which was this if statement, where I think I would say the actual smell is something different. Yeah, this one.
This one.
I would say when I see that, the smell isn't the length of the if statement itself. Okay. I mean, considering your problem is that complicated, then maybe your condition is really long. But what's missing here, and what I would say I would want to see, is that this if statement doesn't actually capture the problem. What I want to see here is some function that implements a rectangle, circle, intersection test in its geometric generality. Yeah. Preferably not inside the if statement. And exactly, but maybe even like a rectangle and a circle, right? Yeah. Exactly. So in the same kind of was before this, I think there was building this table and you have insert text and insert block and something. Yeah. There's something missing in the abstraction. There is a data structure in there, slide 6, I think.
I know which one you mean, yeah?
Well,
this one.
This one, exactly, right? There's a data structure in there that captures the problem. Something, I don't know what, text and lines or something. Yeah. So this is maybe what I would say the smell is. Write the problem with the abstraction that best describes the problem, right?
So I really enjoyed the talk. I have a question about the for loops versus ranges. Don't you think it's a matter of getting used to one of the methods that you are using? So in time, when we start using ranges more, you get used to the syntax of ranges and you will be seeing them as more natural than for loops.
I guess we should treat ranges as more natural than for loops in any case, except in those very, very simple cases where just a for loop with 2 lines or 3 lines is just plain out to see what's happening there, instead of having like a range that are for more general cases for larger loops or for replacing larger loops where you have to like write more boilerplate to get your things into the ranges. Especially all those lambdas. I mean, I put those lambdas inline into the ranges. You can go ahead and maybe even improve readability. Let's see. Here in this case, you can improve readability if you take those lambdas and make them extra variables with a meaningful name. So, for example, then you have like employees filter, not a manager, and then transform to name and salary or something like that. But this might be actually an improvement over this range. So the difference between the ranges algorithm and the actual for loop isn't that big anymore. But you still have to define those lambda at some point.
Hi Arne, thanks for the talk. I have like these 3 questions. Maybe first one, you mentioned Martin Fowler. Have you had a chance to read his 2nd edition of Refactoring, or first one, and what do you think about this book? Will you recommend to read it for developers?
I haven't actually read the refactoring book. The refactoring book by Martin Fowler, you mean?
Yes.
I haven't actually read it, but I've only heard good things about it. So I'm still considering reading it myself someday.
Yeah, because I heard there is this 2nd edition. I was just wondering if you had a chance or anyone to read this from 2018. But yeah.
Okay, no, I haven't read it.
So I understood that you took this SFM library as a purpose for exploring these code smells, which is made perfectly sense to me from like exploring them. But have you had the chance to see that code smell also is more recent open source code bases like this Foley or other GitHub ones? I'm just wondering if these code smells are still very frequent in nowadays.
Well, some of these code bases have been put up or very recently or are still in development. I know, for example, that SFML is under development still, and I think they are starting the next minor release around end of this year or beginning 2020, where they want to migrate to C++17. So these are current code bases, not something that has been out of development for years. And especially those first code smells like long functions and nesting and so on, you find them all over the place in all kinds of code bases.
Okay, thank you.
Hi. One point that I didn't hear and I would like to mention with the long functions is that they kill testability. So if one was to develop test-driven development, using test-driven development, those small functions and checks like paddle hits the target or whatever would come out of the process very easily. Whereas if it's one long function, it's not testable.
Absolutely, I agree. Usually those long functions and this kind of stuff, it's not written like from the bat in one big piece of code, but they usually start small and then grow and grow, and you might have like tests for the initial function and then you like augment the tests and put more functionality into the function. But I totally agree, like splitting up into smaller functions makes the whole code more testable.
Hi.
Hi.
So thank you for the talk. I really enjoyed it.
Thank you.
And I want to ask for advice on a different code smell.
Okay.
I don't know if it qualifies as a code smell, but the const expr feature in C++17, we can mark a lot of functions const expr because just we can.
Yes.
So, but if in my code base I never executed ever in a const expr context, should I declare the function const expr? Because I might. So does it qualify as a const expr less code smell or rather a premature generalization?
So I sadly don't work that much with C++17, so I'm myself not in that situation, but from what I hear and from what people say, yes, you should, because you give the compiler the opportunity to maybe optimize it at compile time. if you like call it with const expr values, then the compiler can actually go ahead and replace a complete function with just the value that is computed at compile time. And that way you enable this kind of thing and don't, well, miss out on the opportunity. So yes, I would say if you can make it const expr, make it const expr.
Thank you.
Welcome. Okay. Thank you very much.